Welcome, my dear students, on a new lecture on functional analysis. So, we will start a new module, module 4. So, this module deals with defining or understanding certain classes of operator and some properties of those operators. The important class of operator is the Hilbert adjoint operator. So, in the previous result, associated with a SQL linear form, H from H1 cross H2 to K, we have defined an operator H of xy, which should be of the form inner product Sxy. This S is actually a map from H1 to H2, which is a bounded linear operator and it should be unique. And also, if we consider the reverse part, a map from H from H2 cross H1 to K, similar assumption also holds. H of yx should be of the form some inner product ty x, where t is a map from H2 to H1. Now, the natural question is associated with this SQL linear form, which is defined from H1 cross H2 to K, and another SQL linear form H, which is defined from H2 cross H1 to K, we have two different maps. One is a bounded linear map S from H1 to H2, and the other one is a bounded linear map T from H2 to H1. Both of them should be unique. Now, if you consider this case to be a real field, then H of xy and H of yx should also be same, because it should be the conjugate. In the case of real numbers, the conjugates are actually same. Now, the natural question is there any relation between this S and this T? Because associated with this H, we have defined an S. Associated with this H, which is defined on H2 cross H1, instead of H1 cross H2, we have defined a T. Does there exist any sort of relation between this S and T? Or is there any spaces in which this S and T are related by some operation? So, we have already discussed that this H of xy, if the space or the field is actually real numbers, H of xy conjugate should be equal to H of yx conjugate should be equal to H of yx, which should be equal to inner product tyx conjugate, which should be equal to inner product xty. So, H of yx and H of xy in some sense can be related, or we are trying to observe is there any particular relationship between a SQL linear form H1 cross H2 and its associated unique bounded linear transformation and a SQL linear form which is defined from H2 cross H1 and its associated bounded linear form T. So, this is our observation. Some cases we can somehow define a relation connecting these two. Such type of operators are called Hilbert adjoint operator. This is the general sense. Now, using Hilbert adjoint operator and its properties, we can define three different classes of another operator, which we are going to study in this module. The operators are self-adjoint operators. Next is unitary operators. Next is normal operator. So, associated with the Hilbert adjoint operator, we can define three different classes of operators: self-adjoint, unitary, and normal operators. And in this module, we will discuss the properties of all these set of operators, and also we will discuss some classic results regarding Hilbert adjoint operator. Okay. Now, using this operator, we can classify and we can quote certain result. Three of the classic results in this function analysis, they are Hand-Banach theorem and Bayes category theorem and uniform boundedness theorem. So this module deals with these four operators and these three theorems. The main concepts of this module are the four operators: Hilbert adjoint operator, self-adjoint operator, unitary operators, normal operator and its properties. And using these four operators, we can define or we can understand three classic theorem in function analysis. They are Hand-Banach theorem, Bayes category theorem, and uniform boundedness theorem. Now let's go down to the main contents of this module. So this is the summary of this module in general. So first is Hilbert adjoint operator. As I have already told you, this comes from the motivation. It is obtained from the recess representation theorem, which states that associated with a sesquilinear form, there exists a bounded linear operator. And if you define a sesquilinear form in H1 cross H2 and H2 cross H1, we get two sesquilinear form. Associated with these two, we have two different bounded linear operator. And can we relate this operator using some sort of relation? Because this sesquilinear form has the inner product notation. So there should be some sort of relation, at least in some classes of spaces. So this motivates us to define a new class of operator called Hilbert adjoint operator, which is defined as. So the Hilbert adjoint operator is defined as, let T from H1 to H2 be a bounded linear operator where H1 and H2 are Hilbert spaces, and associated with T, which is defined from H1 to H2, then we can define another operator, if at all possible, to define another operator T star, which is defined from H2 to H1, such that for all x element of H1 and y element of H2, inner product Txy should be equal to inner product x T star y. If such an operator exists, then T star is called the Hilbert adjoint operator. So, associated with a bounded linear operator, if at all there exists another operator T star which satisfies this condition, inner product Txy should be equal to inner product x T star y, where T star is a function operator from H2 to H1. If such an operator exists, then we call T star to be the Hilbert adjoint operator of T. So although we have defined the Hilbert adjoint operator, we do not know such an operator exists in the case of a general bounded linear operator. So first we have to establish the existence of such an operator, the existence of a Hilbert adjoint operator for a arbitrary bounded linear operator. So that's the first thing, the existence of T star, which is what we are going to establish in the next result. So we can formally quote the existence of the Hilbert adjoint operator as a theorem. The Hilbert adjoint operator T star of T, where T is a bounded linear operator, always exists, which means that associated with every bounded linear operator, there should exist its Hilbert adjoint operator, and it should be unique. So which means that associated with every bounded linear operator, there should exist a unique adjoint operator, and the Hilbert adjoint operator is again a bounded linear operator and has the same norm. So associated with a bounded linear operator, there should exist its Hilbert adjoint operator, which should be unique, which is bounded, and which is linear and has the same norm. So these are the fundamental characteristics of the Hilbert adjoint operator, which is associated with a bounded linear operator in general. So let us prove this. So what we have to prove is, we have to prove that associated with this bounded linear operator, there exists a Hilbert adjoint operator first. Then we have to prove that such an operator should be unique. Then we have to prove that it is bounded, linear, and has the same norm. So these are the things which we need to establish. Let us move on to the proof. So proof is, so given that T is a bounded linear operator, and associated with T, we define as a squilinear function H from S2 cross H1 to K, defined by H of Yx should be equal to inner product Y Tx. This is equation number 1. Now we have to prove that this is sesquilinear. So it have to be linear with respect to the first component and conjugate linear with respect to the second component. So we take h of alpha y1 plus beta y2 x should be equal to inner product alpha y1 plus beta y2 comma tx. This by definition of inner product should be equal to alpha y1 comma tx plus beta y2 comma tx. This should be equal to alpha times inner product y1 tx plus beta times inner product y2 tx. This by definition is inner product, this is h of yx, y1x, this is h of y2x. So alpha times inner product h of y1x plus beta times h of y2x. So we have proved that h is linear with respect to the first component, that is h of alpha y1 plus beta y2x is equal to alpha times h of y1x plus beta times h of y2x. Now we have to prove that h is conjugate linear with respect to the second component. So for that we take h of y comma alpha x1 plus beta x2. This by definition of h is equal to y comma t of alpha x1 plus beta x2. Now t is actually a linear. So linear operator means this is y comma alpha times tx1 plus beta times tx2, because t is linear. Now use the property of inner product. This is actually inner product y comma alpha tx1 plus inner product y comma beta tx2. Now take the second part outside, the constant. If you take the second constant outside, you have to take the conjugate by the property of inner product. So we can write this as alpha conjugate inner product y tx1 plus here also beta conjugate inner product y tx2. So this should be equal to alpha conjugate This is h of y x1. This is beta conjugate h of y x2. So h is linear with respect to the first component and h is conjugate linear with respect to the second component. So which means that h is sesquilinear. In order for S to become sesquilinear, it has to be linear with respect to the first component and conjugate linear with respect to the second component. So H is a sesquilinear function defined from H1 cross H2 to K. Now we will prove that H is bounded. So in order to prove that H is bounded, we take modulus of H of xy. This is modulus of inner product. So this is inner h of y. So h of yx, modulus of it, h of yx should be equal to modulus of inner product y tx. Now by Schwarz inequality, this can be less than or equal to norm y times norm tx. By Schwarz inequality. Now this should be less than or equal to norm y times norm t times norm x since t is bounded. So we have used Schwarz inequality and the fact that t is bounded. T is bounded means norm of tx should be less than or equal to norm t times norm x. Okay. Now, so from this, by definition of h, h of yx should be less than or equal to norm t times norm y times norm x. This means that h is bounded by the definition of boundedness of sesquilinear form. Or we take x and y to be non-zero, then divide with by norm y into norm x. So modulus of h of yx by norm y times norm x should be less than or equal to norm t, which implies its supremum should also be less than or equal to norm t. So supremum x not equal to 0, y not equal to 0, modulus of h of yx by norm y times norm x should also be less than or equal to norm t. This is by definition means that this is norm h. So this is actually equal to, this implies norm h should be less than or equal to norm t. So this is equation number A. So h is bounded and also we have established that norm h should be less than or equal to norm t. Now we prove the reverse inequality. For that, norm h should be equal to supremum x not equal to 0, y not equal to 0, modulus of h of yx divided by norm y times norm x. This should be equal to supremum x not equal to 0, y not equal to 0, modulus of inner product y tx by norm y by norm tx. So norm x. Here it is norm tx, not norm tx, it is norm x. Now, so this is the supremum over all y. Now, if we take y as a particular value, supremum should be greater than its particular value. So we take y as tx. So supremum over all y should be greater than supremum over a particular y is equal to tx. So this should be greater than or equal to supremum x not equal to 0, y not equal to 0, tx by norm tx times norm x. Okay, so norm h should be greater than this, and norm tx should be inner product tx should be equal to norm tx the whole square. Our modulus of norm tx the whole square should be equal to norm tx. So this should be equal to norm h should be greater than or equal to supremum x not equal to 0, y not equal to 0. This is inner product tx which is norm tx the whole square divided by norm tx times norm x. Now we can cancel norm tx. So this should be equal to supremum x not equal to 0, y not equal to 0, norm tx by norm x. So here there's no y, so we should not consider y. So this should be supremum x not equal to 0, norm tx by norm x, which by definition is equal to norm t. So we have successfully established that norm h is actually greater than or equal to norm t. So norm h is actually greater than or equal to norm t. So this is equation number B. So from the first two equation, norm h is less than or equal to B, norm h is greater than or equal to B implies norm h should be equal to norm t. So we have established norm h should be equal to norm t. Since we have already established that h is sesquilinear and h is bounded. So h is sesquilinear and h is bounded, which implies by Riesch's representation theorem, so we can write it as by Riesch's representation theorem, h can associated with h, where h is from h2 cross h1 to k. Associated with this, there exists a linear map, bounded linear map, unique bounded linear map from h2 to h1. So T star is bounded, T star is linear, and T star is unique as well. So these three conditions has been satisfied. So such that h of yx should be equal to inner product T star y x. This can be obtained from Riesch's representation theorem. H is a sesquilinear function. H is bounded, which is defined from h2 cross h1 to k. Then associated with that, there exists a unique bounded linear transformation T star from h2 to h1, which satisfies h of yx is equal to inner product T star y x. So this has been satisfied. Okay. Now, using this Riesch's representation theorem, we have norm of T star should be equal to norm h. And we have already established that norm h should be equal to norm t. So this should be equal to norm t. So thus we can conclude that norm T star should be equal to norm t. This was the first property which we needed to establish. Now we have to prove that this T star is actually the Hilbert adjoint operator associated with T. In order to establish that, we have to prove that inner product Txy should be equal to inner product x T star y. So we have proved that T star is bounded, linear, and norm of T star should be equal to norm of T. Now the only thing which remains to prove is T star is a self-adjoint operator. So for that, we have we have already assumed that h of yx should be equal to inner product ytx. Now we have assumed that this h of yx should be equal to inner product t star y x. Okay, this is our assumption, and this is what we have obtained right now. Now taking the conjugates, we get this. So if these two numbers are equal, then the conjugates are also equal. So inner product y tx conjugate should be equal to inner product t star y x conjugate. So by the property of inner product, this can be written as inner product txy. This should be equal to inner product x t star y. So this is true for every x, for all x element of h1 and y element of h2. So thus inner product txy should be equal to inner product x t star y, which by definition means that t star is the Hilbert adjoint operator of t. So t star is the Hilbert adjoint operator of t. Okay, so thus we have established that t star is the Hilbert adjoint operator of t, and t star is unique, t star is bounded, t star is linear. So T star satisfies all the condition which we required. Also, norm of T star should be equal to norm T. Thus, we have established that associated with the bounded linear transformation, there exists a self-adjoint linear transformation T star which is unique, which is bounded, and which has the same norm as T. So these are the essential conditions. So this establishes the existence of a Hilbert adjoint operator associated with every bounded linear transformation. Okay, thank you.